So now we're going to look at supervised learning. We're going to start by seeing some basic concepts in supervised learning, the difference between regression and classification, and we're going to start with a simple regression problem of fitting curves with least mean squares, with minimization of the quadratic error as an example of regression, and also as a way to start to understand some basic ideas in supervised learning. So in supervised learning, we have a set of data that has the label. So these labels are, in our known examples, the values that we are trying to predict. And we will represent them in this way, where x will be a vector of features. These will be the input values for our system and correspond to those things we can easily observe in any example. For example, suppose that we wanted to make a system to help diagnose people with some symptoms to see what disease they have. So the symptoms will be the features, because this would be what we will always input into our system, and the disease would be the label, the target value that we wanted to predict. So this is what we represent as y. And in supervised learning, we always need to have a set of data that has both the features and the target values, so the x and the y. Note that these may be vectors. So I'm going to do some examples where x is just a single value because it's easier to represent graphically, but x can be a vector with hundreds of or thousands of features depending on the problem. And we're going to assume that somewhere in nature, in the universe, there is some function that maps between the features and the target value. So maps from x to y. We don't know what this function is, but there is some relation between, for example, the symptoms and the disease, or the color values in an image and whether or not it's the image of a cat or something like that. There must be some relation between the features and the target value. The goal of supervised learning is to find from this set of examples that we're going to feed into the learner some function that approximates f. So we have this function that is a function of a set of parameters, because our model has these parameters to help us choose the best hypothesis. And if we instantiate these parameters into that particular hypothesis, then all we need to do is feed in the x and we get the y value. So we want to find from examples this g function that tries to approximate what reality uses to map between these values. And this is supervised learning because as we are adjusting these parameters to try to find the best hypothesis, we can keep comparing what our function is predicting to what the actual values are in our data. So we can supervise the learning process. So the ideal result here would be that we have this g function, this approximation of the unknown f function that works for all possible examples. So not only the examples that we have now, but all examples that we're going to meet in the future. Unfortunately, we only have a finite set of examples. We have this set of examples that we're going to use to train our learner, and this will call out our training set. So the training set is a set of examples we use to give experience to our learner so that it can improve its task. So we will see next week, start to see how we can work with our data so that we can have an estimate of how well our system will perform outside the training set. But for now, we're going to look just at our training set, and we're just going to consider the error, the difference between the predictions and the target values within our training set. So basically, these are two important concepts. The training set is the set of data that we are using to find the best hypothesis. So we have a hypothesis class. This hypothesis class is represented by a model with some parameters, and we are going to use the training set to adjust those parameters. Once we find the best values for those parameters, we have the best hypothesis, and so this will be the final result of the learning process, and it will be the hypothesis that we use to predict new examples. So the training set is a set of data used to find those parameters. The training error or empirical error, which Mitchell calls also the sample error, is the error we are measuring on the training set for each instance of the parameters. So as we change the parameters, we will have different predictions because we are considering a different hypothesis, and this will result into different values of error. So this is the training error that we are computing as we adjust the parameters. So the goal for today, we're going to try to predict as best as possible the y values in our training set. Note that then we are going to need to generalize this for to be able to predict outside the training set, but for today, let's just consider the training set. So the performance that we're going to measure for this task is higher as we minimize the training error. So the lower the error we are measuring on our training set, the better the performance of our learner. And the data that we have is just a set of points for which we have the features, the x vectors, and the target value, the y. Now here I made a distinction between classification and regression, basically saying that classification, we are trying to predict discrete values. So this y is a set of different values, whereas in regression we are trying to predict continuous values. This is one way of remembering the difference, but it's best to actually understand what the two things are to understand why they are different. In classification, we want to split the data into different subsets. So for example, we have mushrooms that are edible or are poisonous. So we are trying to predict one of those two classes. They are discrete values. And what we want to do with our data is to split it into those two sets. So you can think that we are trying to find some frontier that separates the two subsets, and ideally this frontier should be as far as possible from the actual points, so that even small mistakes will not be critical, but because they will not change the class that we assign to each point. In regression, we are trying to predict a continuous value, for example, price trends, probability of people buying some products and things like that. So we want to find a function that approximates as much as possible these target values. So instead of having something that splits the data into subsets in frontiers that are as far as possible from the data points, we want a line that accompanies our data as close as possible to the actual values. So you can see that these are different approaches, different things we're trying to do. So that's why regression and classification are so fundamentally different. But they have one thing in common. We have the target value in our data, in our training set, and we want to supervise the learning of the learner in order to make it improve as much as possible its predictions. We are always comparing the predictions to those labels to see how it's doing. Okay, so let's start with regression and a very simple example of linear regression using polynomials. I'm going to explain why polynomials is linear, even though if we think about polynomials, we can see that they can curve a lot, but I'll explain why they are linear. So basically the idea of a linear model is that you can write it as a linear combination of some input values. But let's start with just a straight line. Suppose that we have a set of points. Each point has one value for the feature, this is the x, and one target value, the y. And we want to fit the best line through these points. For example, these points here that we have. So we want to fit the line to as close as possible to these points. So I have a question from Ruben. With discrete values, it can be splitting data into different categories. Well, I'm not sure about counting, but you can have classification with more than two classes. You can have an arbitrary number of classes. For example, in the handwritten digits problem, you have 10 different classes for classification from 0 to 9. So in all the cases where you want to split your data into a fixed number of sets, whether they are many or they are few, you have a classification problem. because you're trying to separate the data into subsets. In regression, you're trying to approximate the values as much as possible. So in this case, for example, this is a regression problem because ideally we want to find a line that is as close as possible to these points. But since we have this model here with only these two parameters, so our hypothesis class is a set of straight lines, we cannot probably get very close to the points because we are only using straight lines. But even so, some lines are further from the points than others. So if we drew a line here, for example, it would be much farther from the points than drawing a line here. And the problem now is how can we measure the performance of the learner in order to encourage it to find the best line. We need to have some measurement of how good a line is in order to train our system. So let's see one way where we can specify what is a good line or a bad line, or how we can measure how good a line is. Let us assume that in nature, this y value here, so the value in the vertical, is determined by the feature, the x value that we have here, by some function that we don't know. This f function, we don't know what the function is. But in addition, there is also some noise, some random error. So the function determines this y value, but then it can fluctuate a bit around that point. So there is this additional error factor that we're going to assume to be normally distributed around 0. This means that it can make, the error can be up or down, so positive or negative with equal probability, and has a normal distribution. We are going to try to find this function g of x and of these parameters. So in this case, this is our function g. We are going to determine these parameters to choose an hypothesis, but then we can feed in the x and obtain a prediction for the y. And we're going to try to approximate this function to this unknown f function that in reality relates x and y. So we can estimate the probability of a given point that has some value of x having some value of y as being something that is normally distributed around what our function predicts. So our function tells us the point should be some particular value, but the probability of the point having some value should be somewhere higher, closer to that prediction, and lower as we go away from that prediction. So let's assume that we can compute the probability of a point with some x value having that particular y value by estimating that probability from the prediction that we're going to make with our learner. But note that we have these theta values here that we can change, so different hypotheses will give different predictions, will give different probabilities. We also know that the joint probability of having of two variables can be decomposed as the probability of one if the other has this particular value multiplied by the probability of the other having that particular value. So this is a basic relation in probabilities. So basically we can write the probability of our data set having that combination of values as the product of the probabilities of all individual examples in our data set, and this can be decomposed by the probability of having that y value given that it has the x value that it has, multiplied by the probability of having that particular x value. So this is just the expression of how we can compute or estimate the probability of our data if we know these probabilities here, the marginal probability of the features and the conditional probability of the target value if we know the features. So why do we want this? Because we can think of our data as a random sample taken from nature. If we went back in time and repeated our experiments and so on, the sample would be different. So the actual values that we have in our training set are a sample from probability distributions that we obtained from nature. However, the parameters that we are trying to adjust here in order to make our function as close as possible to what nature uses to relate x and y, are not random variables. We are manipulating these parameters and trying to optimize them. So what we want to do here is to find the set of parameters that makes our data as probable as possible. Because if our parameters are too far away from what would give us a good approximation to f, then the line will be too far away from the points, and the probabilities of having those points, if this hypothesis were true, would be low. We cannot talk about the probabilities of the parameters themselves, but we can think about the probability of the points. And this is the idea of maximum likelihood solution, or finding the maximum likelihood solution for this problem. The likelihood of our parameters, or more generally, the likelihood of the hypothesis we're going to choose here when we instantiate the parameters, is the probability of the data coming out like that. So when we sample the data from nature, if the hypothesis is true. So if that hypothesis is true, then the data would have the probability that we can compute in this way. So if we select the parameters that maximize that probability, that is to say, if we select the parameters that have the maximum likelihood, then we get closer and closer, or as close as possible, to the data that we have. So this is what we're going to do. We're going to adjust our parameters in order to maximize the likelihood of the parameters given the data, the training data that we have. So this would be maximizing the probability of the data, assuming each hypothesis to be true, and we can decompose this into the conditional probability of having this y value given the x multiplied by the marginal probability of having those features. We can simplify this a bit if we take the logarithm, because all these products, we can convert them to sums if you take the logarithm, and the maximum likelihood solution, that is the set of parameters that maximize the likelihood, will be the same that maximize the logarithm of the likelihood. So taking the logarithm changes the actual value we are computing, but does not change the set of parameters that maximize this. So we can do this and still obtain the same solution in the end. And since this part, the probability of having specific x values here, so these x values of all the points, the probability of this has nothing to do with our function, because we are trying to compute y from x, and we are not trying to compute the probability of x. So we can ignore this part here. As we change our parameters, theta, we are going only to change this term. So we can basically consider this to be a constant, and since we are trying to maximize this function, we can throw away the constant and just retain the part that we want. So maximizing this, the logarithm of the product of these conditional probabilities, will give us the set of theta parameters that result in the hypothesis for which the distribution of data that we have is most probable. That is, we want the most likely hypothesis. Now we can apply the normal distribution here. Remember that we are assuming that the probability of a point with some value x having some value y is a normal distribution around the prediction that we are making. So if we get the formula for the normal distribution and replace here, this is what we get. And now we have this variance here, this pi, and so on. And all these are constants that we can just ignore, because all we want is the value of theta that maximizes this. So we don't need to carry those constants around, just the part that is actually changing. So simplifying this in this way and taking the logarithms, we obtain this final result. So the logarithm of the product, we convert this into a sum. Since we have the logarithm of this e raised to that value, we simply take this and put it down here, and we can take the minus sign outside of the sum. So if we maximize this expression, we get the theta values that make our data, that give us an estimate for the probability of our data to be as high as possible. And so this is the maximum likelihood solution for our particular model. And if you see, what we have here is the quadratic error. So basically, if we try to maximize minus the sum of this is the same as minimizing this. So you just change the sign. Maximizing something with this sign, you change it and becomes a minimization. And this is the difference between what the value should be and what we are predicting the value to be squared. So basically, it's the square of the difference between each prediction that our system is making and the value that we have in our data. So this is the quadratic error, and the sum of the squared errors, the quadratic errors, is what we're trying to minimize in order to fit our data. So this is something that you're going to find a lot, because this quadratic function becomes very simple to minimize. The quadratic error is very simple to understand and very, very clear. And so in many cases, when you fit curves to data, when you do this kind of regressions, you will end up using this least mean squares method, which is minimizing the quadratic error. But the important thing here is to understand where this comes from. This is the maximum likelihood solution when we assume this part here, that the error is only affecting the value we're trying to predict, and it's normally distributed around our prediction. This is what will end up becoming the minimization of the quadratic error. So if we assume this, then it becomes very easy to find the best parameters, at least in theory, because the function is well behaved and can be solved relatively easily. But we are assuming this implicitly. So remember that if you have some problem where these assumptions don't hold, for example, you have error on the x, or the distribution of the error is not normal, something like that, then everything may become different in these derivations. So remember that minimizing the quadratic error is a very useful and very widely used approach to regression, but it assumes this normally distributed error around the predicted values. Okay, so let's see how we do this. This is called least mean squares minimization. We're trying to find the value of our parameters that minimizes the quadratic errors, and this will be the criteria for finding the best line. So let's suppose that we are looking for the best line here. We have an infinite class of hypotheses with all the straight lines that we can draw, and we can represent these lines with this model. So we have two parameters, θ1 and θ2, that specify the slope of the line and the intercept of the line, and this way we can draw any line that we want. And we want to adjust these parameters in order to minimize the quadratic error, the total quadratic error, between what our model is predicting for each x and what the y should be. So the y, the target values, are the red dots here, and the predictions are the line depending on the theta values that we choose. So we can visualize this surface, this quadratic error, as a function of the two thetas. So let's say this is θ1 and θ2, and as we change the values of the slope of the line and the intercept, the error may become higher or lower as we move further apart or closer to our set of points. So the minimization process here, which we are not going to look into detail because we're going to use the libraries that already have this implemented, but the idea is that it will start from some random point and then check the derivative of this error and slide down the error surface until it reaches a local minimum in some direction. Then it will change direction and repeat the process, and it will do these sort of things by wandering around the surface, but always trying to go down until it finds the best spot, so the spot where the quadratic error is minimized. And one reason why least mean squares optimization in this case is very useful is because of the shape of this function. So this quadratic function has a very nice shape for minimization. Okay, so this allows us to find the best line. This is the best line we can find, the one that minimizes the quadratic error, or the one that maximizes the likelihood under that assumption of a normally distributed error on the y value here. So this is not a very good fit to this data, but the reason it's not very good is because we are only considering straight lines, and obviously our data is not very straight. So our model doesn't seem to be very good because it only represents straight lines. Our hypothesis class is only of straight lines, so it's not a good fit for this data. So how can we generalize this and try to fit a curve to this data? We can keep using linear models. So a linear model is a model where the output is a linear combination of the input, but we can change the data. Let's apply a nonlinear transformation to our data and create a new data set that now is in 3 dimensions. We have 2 values for the features, and the third value, the third dimension, is the target value that we want to predict. And our features will be x2 will be just the same as the original, just the original x, and x1 will be the square of the original. So we can take our data, compute the square of x for each data point, and create a new data set that now is something like this. These are the 2x, so x1 and x2 here. x2 is the original value, x1 is the original value squared. The axis here is a bit more compressed, so I could put the whole image in the same plot. And you can see that now this is curved here. So if we plot the 2 x values for each of our data points, we have this curve because we are using a quadratic function. We have x and x squared, so this curve is basically the quadratic curve here. And now for each data point in this new set, we have the original y value represented here in vertical. So all these points here go up and down exactly like before. So this is the same data set here, but now they are in a curved surface like the wall of a barrel in this plot in 3 dimensions. And now we can apply a linear model to this problem. So let's take a linear model, which is simply a linear combination of the features. This is an extension of the straight line we used, but in this case, this represents a plane. So we have these 2 thetas for the slopes in different directions, and we have the intercept of the plane to say if the plane is higher or lower, and we can use this model to describe any plane in this 3-dimensional space. And now we're going to do the same thing that we did before. We're going to assume that there is a random error in the predicted value here, and we're going to change these parameters until we find the solution with the with maximum likelihood. So the plane that fits closer to these points. So if you can imagine, these points go up and down, but they also go a bit around in this round shape here. So like a bent sheet of paper in this way. And we are placing this plane in order to pass as close as possible to all these points, minimizing the quadratic error. So now, if we project this back to the original data, because now this x1 is simply the square of x, and this x2 is the original data, we are making the intersection of this plane with this curved surface where all our points lie in this 3-dimensional space. So this is actually a curve because we are intersecting this curved surface with the straight plane, and this is the result that we have here. Okay, so this is a very roundabout way of doing basically a polynomial fit. We are fitting a 2nd-degree polynomial, and if you want to do this in Python, you just need to import NumPy. You load the data, so in this case, this is the text file with the data separated by semicolon. You can use this load.txt function from NumPy and get this into a NumPy array, a matrix with the data. The first column has the x values and the second column has the y values, so I can separate these into 2 variables. This is we can slice the matrix in different dimensions, so it means I want all the rows and the first column, and all the rows in the second column in the second example. And then all I have to do is call from NumPy this polyfit function, where I give the x, the y, and the degree of the polynomial, and it will give me the coefficients for the polynomial that minimize the quadratic error. So this is very simple to do in practice. This is a polynomial regression, but the reason why I'm talking about this in this way is because I'm showing you the equivalence between doing the polynomial regression or doing a transformation, a non-linear transformation of our data, doing simply a linear regression in that space with more dimensions, and then going back to the original dimension. And the reason I'm talking about this is that we're going to see this recurrently in different models in machine learning for classification and so on, because we can use a simple basic linear model, but then transform our data as we need in order to make it more powerful and able to deal with other hypothesis classes and so on, and adjust our data better. So this is the idea. We are implicitly creating a new data set where we use x squared and x and doing a linear fit there with this plane, but we can do this by calling polyfit and then representing the image. By the way, the rest that you have here is just to draw the figure. So what we need is, when we do a plot, in this case I'm plotting the data, the x values, the y values, and then red circles. So I put an O and an R there. The O is the shape of the circle, the R is the color, and this draws all these little circles here in red. But I also want to draw the result of the fit, so this curve. And when you plot something with a line, matplotlib, so pyplot, will join the points together with straight lines. If you want to do something that looks like a smooth curve, you need a lot of points. So this is what I did here using linspace. This is a function that returns an array of values that starts at the first argument, ends at the second argument, and has as many points as the third argument specifies. So this is 100 points from 0 to the maximum value of x. And this gives me a set of 100 points here, for which I can compute the y value, giving the same polynomial that I obtained here. So polyfit minimizes the quadratic error and gives me the coefficients here, the coefficients for the polynomial. Polyval receives the coefficients of the polynomial and an array with the values of x, and computes the value of y for each value of x. So this is what I use to draw the line here. Okay, so this is just an example. You will today or this week in the tutorials, you will start with these kind of simple examples so that we get the basic Python out of the way, and then it makes it easier for you to look at the data, look at the results, and so on. This part here is just setting the title, and savefig allows you to save the image to either JPEG, PNG, or something like that. So this is useful if you're putting it into some report. Otherwise, if you just want to see it on the console, you can do it like this, and then it will pop up in the console. Okay. I add close. If you do a lot of them, you should close them so that they don't take up memory. And if you don't want to see them appear in the console, you can close them. If you omit close, then in this case, it will save the figure and then appear on the console. But you can experiment with this if you want to do this plot. So this is the basic idea, is that it's very simple to do a polynomial fit with least mean squares, so minimizing the quadratic error, just by using this polyfit function from NumPy. You get the coefficients of the polynomial. And an important concept here is that what we're actually doing, we can think of it as transforming our data into a higher dimensional space by using x and x squared and eventually x cubed, fourth, and so on, and then fitting a hyperplane into that space and coming back to the original space of our data. So if we do this, we can actually start curving more. So in these cases, we started with this assumption that we can adjust the data with a straight line. but now we can choose different polynomials. So for each degree of the polynomial, we have a different assumption that we are considering. We can adjust our model to the data by using, for example, a polynomial of degree 3 or degree 4 and so on. By choosing the degree, by choosing the model that we have, we can then instantiate into specific polynomials in that hypothesis class. So by changing the degree here, we can move through different hypothesis classes from which the best hypothesis will be chosen. And since we have this idea that we can keep using a linear transformation, a linear model, but on a higher space after doing some nonlinear transformation with our data, we can apply this in many different cases. So as long as we can work with a linear model, then just transforming our data adequately can help us allow us to cover many different hypothesis classes. So basically, different hypothesis classes, we can think of them as polynomials of different degrees or straight surfaces, hyperplanes in higher dimensions. The set of planes in 3 dimensions would be one hypothesis class. The set of hyperplanes in 4 dimensions would be another, 5 dimensions another, and so on. So if we transform our data non-linearly, then we can access those different hypothesis classes, and it will make a difference in how we fit those models to our data. So let's see some examples here. We can go to degree 3. So this is a polynomial fit of degree 3. We are computing these 4 coefficients. Or if you want to think about it a different way, we are using a 4-dimensional space for our data. So 3 dimensions of the features, and then the 4th dimension is the target value that we want to predict. And these coefficients determine a 3-dimensional hyperplane inside this 4-dimensional space. Of course, this I cannot represent. We cannot see very well in 4 dimensions, but you can think about it in that way. And this will give this result. So this is the best fit using a polynomial of degree 3. We can go higher. For example, degree 5 will give us this here. Or, for example, degree 15. We can have all these 16 coefficients, adjust everything using up to powers of 15th power for x, and we get this result here. So one thing to note is that the higher we are going with our polynomial, the closer we can get to the points. So you see, when we reach 15, we are passing really, really close to the points. So it seems that we are improving our fit. We are going very, very close to the data that we have. On the other hand, this starts to give us some pretty silly results. For example, looking at the pattern of our data, of the points that we know, it doesn't seem reasonable to predict that if the x is around 3, y would be all the way down here instead of somewhere between those points. So this is, you can see a problem here. It's very easy to increase the power of adjusting our curves to the data by using models that are more powerful, more flexible, and can give us this result. So if we go to a polynomial of degree 15, we can really go very close to all the points. However, when we start doing that, we start losing the ability to predict values outside the training set. So for the values that are inside the training set, prediction seems to be very good, but outside the training set, we start getting things that are not reasonable. So this is a problem that we're going to start looking at next week, which is how far should we go here and how can we evaluate when this starts to appear. So basically, this is the overfitting problem. We are choosing a hypothesis that is very well adjusted to the data that we have, but it's too much adjusted to the data, and it starts to represent things that don't generalize, that are not true outside the data that we have. So it's possible to have a very small training error on the data that we're using to choose the best hypothesis, but still have very large error outside the training set. And this is something that we need to prevent because we cannot judge the quality of the hypothesis simply looking at the training error if we want to predict something outside the training set. So that's what we'll start looking at on the next lecture. So for today, we saw these basic notions of supervised learning and the difference between classification and regression. And we started looking at linear regression. So solving a regression problem where we're trying to predict a continuous value using a linear model, a model for which the output is a linear combination of the inputs. And we also saw two important things here, which is how we can choose the best hypothesis, minimizing the quadratic error. This is a result of assuming that the error is normally distributed and is affecting the variable we're trying to predict. In that case, the maximum likelihood solution will be the minimum of the sum of the quadratic errors. And we also saw that we can fit curves with polynomial regression, for example, by using implicitly a linear model in higher dimensions, but after doing some non-linear transformation of the data. So we are transforming our data into higher dimensions and twisting the data, reshaping the data, and then when we fit something straight in that higher dimensional space, it turns out to be something curved in the original space that we have. So polynomial regression is an example of that, but we're going to see this idea recurring many times along the course. And to finish, we saw that we can go too far with this. If we increase too much the power of our model, we start learning things that we shouldn't. We start fitting too much to the data that we have, but then lose the ability to predict outside the data. So this is the problem of overfitting that we're going to cover next week. I recommend that you read chapter 1 of Bishop and these sections of Alpiden and Marsland, besides the lecture notes and the slides for this part of the subject matter. And now, in a couple of minutes, I'll just turn this off and log into to Colibri, and I'll start the session on Zoom. So if anyone has questions, you can join me there in the Zoom session, and we can talk a bit about these things. Okay. So see you soon.